discuss motion curves. It is often useful to utilize pictorial representation of kinematics using graphs, especially when the position of an object can be described by a differential equation of a curve. Take note that in mathematics, a line is considered a first-degree curve. In kinematics, we are basically curious about three quantities. First one is position. Second, velocity. This describes the change in position of an object or a particle being considered over a period of time. We have acceleration, which then describes the change in velocity of an object over a period of time. If, for example, you have the acceleration differential equation of a curve, or a graph that represents the acceleration of an object with respect to time, or in terms of time, and you want to look for the velocity time graph. And from the velocity time graph, you want to look for the position time graph of the object. The process that you will do is what you call your integration. If you have the position time graph of an object and you want to look for the velocity time graph, then the acceleration time graph of the object, then you will use the process of differentiation. Let's have this example for the motion of an object with constant velocity. You have your time in the horizontal axis and position s in the vertical axis. We have this line that can be written as y equal to mx plus b, wherein m is equal to the slope of the line. Now, from this position time graph, if you will differentiate the equation of this line with respect to time t, then you will arrive with the velocity time graph. Now, naturally, if you will differentiate y is equal to mx plus b with respect to x, or the x-axis, in this case that is t, then you will have y prime equal to m, or basically the constant, as shown here in the graph of the velocity time, wherein the velocity as time changes is a constant. And if you take the differential, or if you differentiate the velocity, constant velocity, with respect to time, then you will arrive with zero acceleration. True to what it is, that if there is no change in velocity, there is also no acceleration, because acceleration describes the change in velocity with respect to time. Next is motion with constant acceleration. We have here a second degree curve in the position time graph. Differentiating, you will arrive with the velocity time, and its degree will be first degree. Further differentiating with respect to time, you will arrive with the acceleration time graph. And for this one, you have constant acceleration. Another example, for the motion with variable acceleration, we have here a curve in the third degree for the position time graph. Differentiating, you will arrive with a velocity time graph with the second degree. And for the acceleration time graph, you have here constant increase. Take note that that can also be a constant decrease in acceleration. So those are examples of your motion curves. Now let's try to solve motion curves, or find the motion diagram using area method. We have here acceleration time. Now take note, as we recall, that if you have your acceleration time graph or curve or equation, to find the velocity time graph, you will need to look for or differentiate with respect to time. So we have here the red line is describing the change in acceleration over a period of time. So we have here your first acceleration or initial acceleration and your final acceleration. and the difference between the time intervals. Consider a given AT diagram. That acceleration would be equal to the slope of the velocity time graph. A is given, therefore it is constant. A is equal to dv over dt. And if you cross multiply A times dt, you will arrive with dv is equal to A times dt. And integrating that equation, you will arrive with Vn minus V0 is equal to A times Tn minus T0. And this difference between the velocity is equal to the area of the AT diagram from Tn to T0. Similarly, you have V is equal to ds over dt, that is equal to the slope of the ST diagram. V is a given, therefore it is constant. V is equal to ds over dt. And doing the same process, we integrate. We have Sn minus S0 is equal to the area of the Vt diagram from Tn to T0. So, let's have this example. Given AT diagram, we are asked to plot the Vt and St diagram. At t is equal to 0, velocity is equal to 0, and the position S is also equal to 0. We have this given. For this example, we were not given the equation of the acceleration time, but instead we were given the diagram right away. So we have here, you're given the AT diagram of the motion of the object. So we divided it into two parts. The first is the rectangular part and the triangular part, for us to easily compute for the areas of these graphs. So we are asked for the velocity time diagram and the position time diagram of the motion. So from our previous discussion, we have determined that the area of the AT diagram from Tn to T0 is equal to the change in velocity of the object. So let's consider this green area first. So that would be, the acceleration is in terms of meters per second squared and time is in terms of second. So for the area, that would be 4 meters per second squared multiplied by the interval of time, that would be 2 seconds. This would be equal to 4 times 2 is 8 meters per second. That would be the change in the velocity of the object. For the triangular part, that would be equal to 1/2 times base, which is from 4 to 2. So this, we are only considering 2 seconds, not the total of the 4 seconds, because we are considering the time interval. So this would be equal to 2 seconds times the height of the area, that would be 4 meters per second squared. So this is equal to 4 meters per second. That is the change of the velocity of the object from time to time equal to 4 seconds. So next, we are now ready to have your velocity time diagram. So we have this here. We have computed for the area of the rectangular part from time 0 to time equal to 2, and that is equal to 8. So that is the height of the velocity. There is a change in the velocity from 0 to 8. And this is a constant slope. So there is also a positive constant increase in the slope of this line. So from 0 to 8, because at time 0, the velocity is equal to 0 meters per second. But if it was noted that at time 0 there is a value for the velocity, then you will start from there. For example, if that is 1 meter per second squared, then you will start from here, and then you will add 8 meters per second. So your endpoint would be here at 9 meters per second, starting from 1 meter per second squared, ending at 9 meter per second squared, because you increased by 8 meters per second. So for the second part of this area, we will start from the tip of your first area. So this would be 4 meters per second. So 8 plus 4 is equal to 12. This is 12 meters per second. Now, how are you going to decide what is the concavity of your curve? In the first part, you have a positive value, positive 8 meter per second squared. Take note that this is telling us the change. So that is positive. This is also positive. And there is a constant slope. So the slope of the increase of the slope here is also constant. While for the second area, you have a positive increase, but the slope is decreasing. So from a larger slope, you have here a larger slope or higher value of slope, you increase the value of your slope. So the concavity is this way. So you have now your velocity time diagram. Next, we are looking for the position time diagram of the object. So same process, we have the area of the VT diagram from Tn to T0 is equal to the change in the position of the object. So for this area, that is equal to 1/2 times 8 meter per second times the time interval 2 seconds. So this would be equal to 8 meters. And for this part of the area, to easily solve this, let's try to divide it into two parts. The first one is the rectangular, and we have here the parabolic segment. So this is of second degree. This is first degree. This is constant, so there is no, that is 0 degree. And this is first degree. So we are integrating here because from acceleration to velocity, that is integration. So for this area, that would be 8 times the interval of 2 seconds, that is 8 meters per second times 2 seconds. That would be equal to positive 16 meters. For this one, that would be 2/3 of base times height. The base is 2 seconds and the height is 4 meter per second. Why is that 4? Because this is 8 meters per second for the velocity, and this is 12. The difference between these two, or the length of this line, is equal to the difference between 12 and 8, that is 4 meters per second. So this is equal to 16/3 of a meter, positive, because that is in the positive plane. Next, we add these two values for the change in the position of our object. That is 16 plus 16 thirds, and that is equal to 64 over 3 meters. We are now ready to plot the position time graph. This is 1, 2, 3, and 4 seconds. This is 5, 10, 15, 20, 25, and 30 meters. So this area from the velocity time graph is equal to the change in the position of the object. And our starting point for this case would be at t is equal to 0, the position of the object is at 0 meters. So we started at 0 meters. Same here in the velocity time graph. If you will start from another position, so for example 5, you will start here and you will add or subtract the area, the value of the area of your velocity time graph in the given time interval. But for this case, we will start at 0. So we will end at positive 8 because 0 plus 8 is equal to 8 meters. So this is 8 meters. For the concavity, this is increasing slope. So from a smaller value of our slope, we will increase in slope. So this is our concavity. From a lower value of slope, we increase in slope. So this is our concavity. And then we will add this value, positive 64 over 3, from the 8 meters. And that would be equal to this one, 88 over 3. That is almost equal to 29.33 meters. For the concavity, this one is decreasing in slope. From a higher slope, it decreases into a lower value of slope. So it will follow the slope of the position time graph. So from a higher slope, we will decrease in slope. So the concavity is this way. So from our acceleration time graph, we have now your velocity time graph and your position time graph. That is how you use the area moment method to find the motion diagrams of the kinematics of an object.